Hi friends, welcome to the new class of Instrumentation System. Now let's see the remaining portions of the topic temperature sensing devices. As we've seen in previous classes, temperature sensing devices are classified into 6. First 4 terms, that is thermometer using thermal expansion methods, thermoelectric sensors, electrical resistance sensors, junction semiconductor sensors, are already discussed with second and third classes. Those who want to go through it can get the link from the description box. Now let's move on to the remaining 2 topics, that is digital thermometers and radiation methods. First one is digital thermometers. We know that industry's most measured quantity is temperature. In most applications, the nonlinearity of thermocouples and resistance temperature detectors is very much great, hence we must use calibration tables to convert voltage or resistance values to corresponding temperatures. If the number of measurements increases, this process of conversion will take much time and even bring the chances for error. Moreover, the reference junction temperature must be calculated if it is not ice point temperature. We have seen that linearization is needed for both thermocouples and resistance temperature detectors. Linearization method may be analog or digital. In digital linearization, it may either non-microprocessor or microprocessor, in which linearization with microprocessor is widely used. Symbol units provide linearization for only a single type thermocouples, whereas linearization with microprocessor allow switch selection from among 6 types and gives readings in Celsius too. Reference junction compensation in thermocouple thermometers usually uses an isothermal block whose temperature is monitored by a junction semiconductor sensor, which sends this data to the same microprocessor that does the linearization. Accuracy of the actual temperature measurement will be considerably less because of deviation of the individual thermocouple or resistance temperature detector from published tables and usual problems of sensing any physical variable precisely. Sharing of a single digital thermometer among many thermocouples or resistance temperature detectors is possible by using scanner accessories. Moreover, interfacing to printers, computers, etc. is also possible as digital information is available already. Next one, radiation methods for temperature measurement. The above mentioned temperature measurement devices are doing the measurement by physical contact with the body whose temperature is to be measured. It has many drawbacks. First one, the measuring device must withstand the temperature to be measured. For high temperature applications, it will create some complexity of melting the device itself. Second one, if the material whose temperature is to be measured is moving, the thermometer must be moved along with the material. This is inconvenient in many cases. Third one, measurement of temperature over a surface is very difficult to carry out. To overcome these difficulties, we may use radiation method to measure temperature, as it does not need physical contact with the material whose temperature is to be measured, and such devices are called radiation thermometers. Radiation thermometers are also called radiometers, radiation pyrometers or optical pyrometers, etc. Radiation measurement instruments can be usefully classified into those that are intended to measure temperature at a point and those that give a temperature map over an extended area, or imagers. Imagers can be further divided into scanning and staring types as shown in figure. Next one is radiation fundamentals. We all know the electromagnetic radiation spectrum. It is represented in this figure. In the order of increasing wavelength, we can represent the spectrum as gamma rays, X-rays, ultraviolets or UV rays, visible light, infrared, radio waves, etc., in which the visible spectrum is quite narrow. 300 nanometer or 0.3 micrometer to 700 nanometer or 0.7 micrometer is the range of visible spectrum. Beyond 0.7 micrometer up to 1000 micrometer is the range for infrared spectrum. Radiation type temperature sensing devices use mainly the range from 0.3 micrometer to 40 micrometer, that is visible light portion and some portion of infrared. Concept of black body. Physical bodies such as solids, liquids and gases may emit electromagnetic radiation for a number of reasons. One of the reasons is temperature. Every body emits radiation depending upon its temperature other than absolute zero temperature or 0 Kelvin. Ideal thermal radiator called black body would absorb any radiation falling on it completely and emit the maximum amount of thermal radiation possible for a given temperature. Let's go to an important video. Any object emits radiation only when the temperature of that object is higher than its surroundings. Like a candle, when we light up a candle, it has a higher temperature than its surrounding room. Similarly, the temperature of the sun is more than its surrounding space. But there is a difference in the radiation of both. Radiation coming from the candle has a wavelength of mostly yellow color, while sun emits radiation of all wavelengths. When its radiation hits an object, it absorbs some part of radiation and rejects back the rest of the radiation. The amount of radiation that an object absorbs is called the absorption coefficient of that object, which indicates how much radiation is absorbed. It can be 20%, 50% or 80%. If 100% of radiation occurring on an object is absorbed, it is called a perfect black body. The absorption coefficient of such an object is 100%. In the ideal case, a black body can absorb the radiation of all the types of wavelengths. Carbon black is an object that can absorb 99% of the incident radiation. Whenever radiation is absorbed by a black body, due to its absorption, the temperature of that body also increases. As a result, the temperature of that body increases in compensation to its surroundings. In this condition, the black body starts emitting radiation. This radiation is called black body radiation. This is not only done by the black body, rather when any object absorbs radiation, it starts emitting radiation itself due to temperature being increased. So any object emits radiation due to the increment in temperature, then the radiation is called black body radiation. Our sun is a perfect black body because it emits radiation of all types of wavelengths. Scientists made a black body in the lab that could absorb up to 99.9% of the radiation. For this, a hollow sphere was taken which has a narrow hole. The inner surface of the sphere is coated with carbon black. When the radiation comes inside through the narrow hole, the radiation hits the wall of the sphere and get absorbed by 99%. The remaining radiation reflects back and collides with wall again. In this way, in each collision, 99% of radiation is absorbed. Due to this absorption of radiation, its temperature also increases. As a result of this, it starts emitting radiation from the narrow hole in which all wavelengths are present. This radiation is called black body radiation. Planck's law, that is, the law governing the black body radiation, states that this equation gives the distribution of radiant intensity with wavelength. That is, the black body at a certain temperature emits some radiation per unit wavelength at every wavelength from 0 to infinity, but not the same amount at each wavelength. This curve gives the relation between radiant intensity and wavelength for different values of temperature. Note that here the peaks are at different wavelengths, and when temperature decreases, the peak occurs at larger wavelengths. Total emitted power can be calculated by measuring the area under the curve. From this figure, it is clear that total emitted power increases rapidly with increasing temperature. Moreover, the vertical distance between the two curves is much greater at short wavelengths such as 2 micrometer than at long wavelengths such as 12 micrometer. This means that the radiation changes much more for a given temperature change at shorter wavelength, making instruments that operate at such wavelengths more sensitive. Next one, calibration of radiation thermometer. We know that black body is an ideal concept having emissivity equal to 1. Real physical bodies can be constructed to approximate closely blackbody behavior. Such radiator sources are needed for calibration of radiation thermometers and generally take the form of a blackened conical cavity of about 15-degree cone angle. It has automatically controlled system with some accurate sensor such as platinum resistance thermometer. It can be used for -20 to 3000 degrees Celsius with a maximum emissivity of 0.999 instead of 1 of blackbody, and the corresponding deviation from the blackbody radiation is expressed in terms of emittance of the measured body. When we discuss complete instruments for radiation thermometry, we will find some are designed to measure at one specific wavelength, others for a specific band of wavelengths, and still others for all wavelengths. This wavelength tailoring shapes the instrument's reading to suit a particular class of applications and is accomplished by the designer's choice of detector, lens material, and optical filters. It also means that any emittance value that we might apply to correct for non-blackbody conditions must be the appropriate type of emittance for a particular instrument. If a radiation thermometer has been calibrated against a blackbody source, knowledge of the appropriate emittance value allows correction of its readings for non-blackbody measurements. Unfortunately, emittances are not simple material properties such as densities, but rather depend on size, shape, surface, roughness, angle of viewing, etc. This leads to uncertainty in the numerical values of emittance, which is one of the main problems in radiation temperature measurement. Real-world objects are characterized by emittance epsilon, reflectance R, and transmittance T, which are related by this equation, epsilon equal to 1 minus R minus T. When R and or T is not 0, we have non-blackbody behavior and measurement errors are possible. Commercial radiation thermometers usually include an emittance adjustment with a range from about 0.2 to 1. Thus, if material emittance is known, it can be compensated for. The most reliable technique for determining emittance for such purposes requires that at some time we be able to measure specimen temperature by some independent means such as thermocouple. Since in this method we are using the instrument itself to determine the emittance, there is no question that we are using the correct type of emittance. The radiometer emittance dial is adjusted until the temperature indicated by the two instruments agree. If there are no changes in conditions, this emittance settings can be used for any future radiation temperature measurement without requiring the presence of the thermocouple. Since emittance can vary with the temperature, such an emittance calibration may be necessary over the desired temperature range. Radiation temperature measurement of plastic films. Plastic film manufacturer makes wide use of radiation temperature measurement and is a good example for emittance consideration based on the previous equation. Reflectance R is about 0.04 for all plastic in the infrared range and is independent of film thickness. Transmittance T is given for cellulose acetate film is measured by a spectrophotometer. Note that in the range 8 to 10 micrometer, film of any thickness between 25 micrometer to 2.5 millimeter behaves almost as a blackbody. Thus, we should design our radiometer for sensitivity to only this range. Atmospheric absorption. Another source of error is the losses of energy in transmitting the radiation from the measured object to the radiation detector. Generally, the optical path consists of some gas, often atmospheric air, and various windows, lenses, or mirrors used to focus the radiation or protect sensitive elements from the environment. In atmospheric air, the attenuation of radiation is due mainly to the resonance absorption bands of water vapor, carbon dioxide, and ozone, as well as the scattering effect of dust particles and water droplets. The absorption effect is shown in this figure. Since the absorption varies with the wavelength, a radiation thermometer can be designed to respond only within one of the windows shown, thus making it insensitive to these effects. Next one is radiation detectors. In all radiation thermometers, other than the disappearing filament optical pyrometer, the radiation from the measured body is focused on some sort of radiation detector which produces an electrical signal in response to the incoming radiant flux. Detectors are made as single elements and also as arrays. A single element detector can be used to measure temperature at a point or as a component in a scanned imaging instrument. Scanned images develop a picture of the temperature distribution over a selected area by using oscillating and or rotating mirrors to deflect the line of sight from target to detector in a raster pattern over a rectangular area. The somewhat complex moving parts are done away within this staring type of imager, where a rectangular array of microdetectors forms the target picture by electronically interrogating each pixel in the array in a sequential manner. Detectors, whether single element or array, may require cooling to reduce electronic noise and increase sensitivity, even though this complication is otherwise undesirable. Cooling schemes include liquid nitrogen divers, which must be refilled every few hours, or thermoelectric coolers or Peltier coolers for non-moving parts, or miniature Stirling type mechanical refrigerators. Various forms of infrared detectors are available for different tasks such as night vision, fiber optic communication, intrusion alarms, agricultural sorting, environmental monitoring, chemical analysis and temperature measurement. Two major categories of radiation detectors are thermal detectors and photon detectors. This is how the thermal images are seen, in which hot items are represented in red and cold items are in blue. Thermal detectors are blackened elements designed to absorb a maximum of the incoming radiation at all wavelengths. The absorbed radiation causes the temperature of the detector to rise until the equilibrium is reached with heat losses to the surroundings. Thermal detectors usually measure this temperature using a resistance thermometer, a thermistor, or thermocouple principle. Photon detectors. Photon detectors are generally based on semiconductor materials. These materials exhibit band gaps, levels of electron energy that are not allowed. That is, some electrons will be found in a low energy valence band, some in a high energy conduction band, but none in the energy gap between the two. To provide an electrical signal, some electrons must be in the conduction band. When the material is exposed to incident photon flux, the individual photons may add enough energy to some of the electrons that they jump across the band gap from the valence band to the conduction band, creating an electrical signal. This general effect is used by detectors in several ways, leading to classes of photon detectors called photoconductive or photovoltaic or metal insulated semiconductor or Schottky barrier detectors. Important radiation thermometers. They are mainly of 6 types: automatic null balance radiation thermometer, monochromatic brightness radiation thermometer or optical pyrometer, two-color radiation thermometer, black body tipped fiber optic radiation thermometer, fluoroptic temperature measurement, and infrared imaging systems. Automatic null balance radiation thermometers. This figure shows an interesting variation of the chopped selective band type of instrument. Here, the rotating chopper exposes the detector alternately to radiant flux from the target and from a feedback controlled reference source. Thus, the detector output signal is a square wave whose mean value is the average of the two flux levels and whose amplitude is their difference. The difference signal is extracted and amplified by an AC amplifier, and the amplitude of this AC error signal is converted to a DC level by a synchronous rectifier. Whenever the reference source radiant flux is not equal to that from the measured target, the error signal drives the reference flux in the direction to null the error. By using sufficiently high gain in the feedback system, the reference flux almost perfectly tracks that from the measured target, and thus measurement of the LED drive signal is equivalent to measurement of the target flux. Such a system is largely unaffected by drifts in detector sensitivity because the detector is located in the forward path of the feedback system. The stability requirements of course are transferred from the detector to the LED reference source, but careful selection and aging gives excellent stability here. The LED response is sufficiently fast that overall system dynamics is determined by the low pass filter required in the demodulator, just as in conventional chopper instruments. This figure also shows linearizing, peak holding and current output features which are not necessary for operation of the basic feedback principle. Monochromatic brightness radiation thermometers or optical pyrometers. The classical form of this type of instrument is the disappearing filament optical pyrometer. It is the most accurate of all the radiation thermometers. However, it is limited to temperature greater than about 700 degrees Celsius since it requires a visual brightness match by a human operator. Monochromatic brightness thermometers utilize the principle that at a given wavelength, the radiant intensity varies with the temperature. In a disappearing filament instrument shown in this figure, an image of the target is superimposed on a heated tungsten lamp filament. The factory calibration of each lamp provides the value of the proper lamp current, which is adjusted with a rheostat and measured with a built-in ammeter. The current and the brightness are then held constant while reading are taken. A master lamp provided with the instrument allows checking at any time to see whether the current needs to be adjusted as the lamp ages or the lamp needs to be replaced with a provided spare. Since the lamp brightness temperature is always the same, an optical wedge is used to adjust the target's viewed brightness so that the human operator can match the brightness of the measured target with that of the viewed filament. A red bandpass filter restricts the matching of wavelength near 0.655 micrometer, the most sensitive region of the human eye. The optical wedge mounted on a rotatable dial inscribed with temperature values is adjusted until the lamp image disappears in the superimposed target image, whereupon the target temperature is read from the dial. If the target is not a black body, tables are provided to adjust for unknown emittance values. Next one is two-color radiation thermometers. Since errors due to inaccurate values of emittance are a problem in all radiation type temperature measurements, considerable attention has been paid to possible schemes for alleviating this difficulty. Although no universal solution has been found, the two-color concept has met with some practical success. The basic concept requires that the radiant intensity be determined at two different wavelengths and then the ratio of these two radiant intensities be taken as a measure of temperature. Special electronic circuitry performs operations equivalent to take the ratio of the radiant intensities. Instruments covering the range 800 to 2200 degrees Celsius are available as standard models. A dual solid state detector is available that allows construction of relatively simple two-color instrument is shown in this figure. Next one is black body tipped fiber optic radiation thermometer. Earlier we mentioned the use of optical fibers to transmit radiation for temperature measurements. In this section, a distinctly different use of fiber optics is the basic of unique new type of radiation thermometer. Originally developed at NBS, it is now commercially available and is intended mainly for the range of 500 to 2000 degrees Celsius in hot gases such as in gas turbine combustors. The sensing probe is made from a single crystal aluminum oxide optical fiber 0.25 to 100 mm in diameter and 5 to 100 cm long. A cup-shaped black body cavity is formed at the sensing tip by vacuum sputtering an opaque 2 micrometer thick film of platinum or iridium which precisely defines the sensing region. The cup-shaped film may have a squared or angled end and use length per diameter ratios from about 2 to 80 with spatial resolution. A protective sapphire film is also formed over the metal sensing film. When the probe temperature rapidly approaches the gas temperature, just as in other probes, of course, conductive and radioactive heat losses prevent the sensing film from exactly reaching the gas temperature. However, the present probe exhibits significant advantages since the conductivity of the sapphire is 14 times smaller than that of typical thermocouple metals, and the fiber's optical transparency cavity projecting radiation characteristic of that temperature along the sapphire fiber toward a silicon photodiode or photomultiplier detector. The sapphire fiber on which the sensing tip is formed can withstand the required high temperature but is rigid and expensive, so it is optically coupled to an inexpensive, flexible, low temperature fiber to transmit the optical signal up to about 100 meter. Fluoroptic temperature measurement. A commercially available fiber optic temperature sensor is the fluoroptic system. Here, a material, magnesium fluorogermanate, activated with tetravalent manganese, exhibiting a long, exponentially decaying fluorescence, either is applied to the surface whose temperature is to be measured or is incorporated into the tip of the probe, which will be pressed against the surface. And the last one, infrared imaging systems. While infrared instruments which measure a point target meet many application needs, sometimes the temperature distribution along a selected line or over a selected area is more useful. Line scanners use a single detector and a rotating or oscillating mirror to scan the detector's line of sight over the target surface, giving the temperature distribution along the scanned line. Such instruments are particularly appropriate for moving targets such as webs of plastic film or huge rotating cement kilns. The scanner gives the temperature profile across the moving web of film during its manufacture, allowing better control of the process. The temperature profile of the cement kiln reveals local hotspots which indicate a need for repair of its refractory lining. For that purpose, both steering and scanning systems are available, but steering systems are preferred in many cases since they do away with the complex moving parts and can often gather more of the available radiation. That is, a scanning system with a single detector element can only spend a short time at any point of the target surface since it must move the line of sight over the entire target quickly enough to complete a scan of about 1/30 seconds. In a steering system, the electrons produced by the incoming photons can be accumulated over a time interval called the integration time by the detector away, since the electronic readout uses a change coupled device or CCD that stores the charge on each pixel's tiny capacitor. This charge accumulation can occupy the entire 1/30 second available between frames for every pixel in the array. The steering instrument referenced here in this diagram uses liquid nitrogen cooling with an indium antimonide detector array to achieve a temperature resolution of 0.02 degrees Celsius. Those who want, just go through these links. Thank you.